So guys, I'm going to go over AMC 10B 2021 fall, numbers 6 through 10. These, it gets a little bit trickier, but again, nothing really too challenging here. Okay, let's see. Problem 6, the least positive integer with 2021 distinct positive divisors can be written in the form m times 6 to the k, where m and k are integers and 6 is not a divisor of m. What is m plus k? All right, well, so in order to really solve this problem, you need to understand a certain rule that comes from number theory, right? Which is the following. So let's say you have some integer in the form n, which has a prime factorization as follows. Let's say it has, so P1 being like, its smallest prime factor to some multiple R1 to the power R1, right? Times P2 to the power R2 times P3 to the power R3, times PK to the power RK, right? So if this is the prime factorization of this number, right? Then we can say, well, how many positive distinct factors does this number have, including one and itself, right? Well, the way you can kind of think about it is that any factor of the number can be sort of built by multiplying some combination of these prime factors. So in other words, you can take some power of P1 up to R1. So from 0, right? Maybe you take none of the P1s up to taking R1 of the P1s as into your factor, right? Same thing for P2. You can take 0 P2s, you can take 1, you can take 2, you can take 3, up to R2. So from anywhere from 0 to that power, you can take that many of that prime multiplied to make your factor. I hope that makes sense. It's a little bit hard to explain, but it's kind of intuitive if you really think about it. So if you think about it, what are the possible numbers of P1 that you can take? Well, you can take anything from 0 to R1, which if you think about it, that's R1 plus 1, right? So you have R1 plus 1 possible values of P1 that you can multiply together to make your factor, right? And then for P2, you have R2 plus 1, because again, 0 to R2. And then R3 plus 1, all the way up to RK plus 1. So essentially what you do to find the number of factors that a number has, you make its prime factorization, and then you take the power of all the primes plus 1 and multiply them together. And that gives you the total number of factors that number has. So in order for a number to have a 2021 factors, right? Well, that means that it's when you break it down to its prime factorization, which let's say is going to be basically 2 to the k times 3 to the k times, now let's say m breaks down as being P1 to the R1, P2 to the R2, P3 to the R3, PK to the RK, right? We can say this is our number that we're trying to find, right? Well, we're going to have to do k plus 1 times k plus 1 times R1 plus 1 times R2 plus 1, right? Has to equal 2021. So it would probably help if we know what the factors of 2021 are. And again, from the last problem, we found out that the factors of 2021 are 43 and 47. 2021 is 43 times 47. So that means we need the product of the powers of the primes plus 1 to equal 43 and 47, right? So how can that possibly work? And we need this to be as small as possible. We want to minimize our number. And we also cannot have any factors of 6 in here, which means no two of the p's can be a 2 and a 3. Like we can't have a 2 and a 3 anywhere in here. We can have a 2, we can have a 3, but we can't have a 2 and a 3 as a factor. Well, if we think about it, since we're trying to minimize this number, what if we probably want to pick 2s, right? So if we have 2 to the k times 3 to the k times, let's make this 2 to the power r1, right? So let's say we want to make let's say we're going to make m just some power of 2, right? Well, then basically this number can be written as 2 to the k plus r1 times 3 to the k, right? And we need these to set up in such a way that one of these would be essentially what, 42, and the other one would be 46. So since r1 has to be positive, then we want k to be 42, and we want k plus r1 to be 46. Well, that makes r1 4, right? So then what does that mean? Well, that means that basically the number that we're trying to find would be 2 to the power 4 times 6 to the power k. K is 42. So the smallest number that we can create that would have 2021 factors that's in this particular form where m cannot be divisible by 6 would be this number, 2 to the 4 times 6 to the 42, right? And the question wants m plus k. Well, m is 2 to the 4, 16. K is 42. 16 plus 42 is 58, which is choice B. That's a, medium, right? Medium difficulty. You need to know that rule about prime factorization to really be able to solve that problem. So I would not call it an easy problem. All right, let's move on to number 7. Now, number 7, if it's the problem I'm thinking of, I can't remember if, sorry, I need to move this out of the way. Yes, this problem drove me mentally insane. I think this was the first problem that I tried to do officially, and it drove me absolutely mental. I was trying to think of a systematic way to do it. I was trying to think of an algebraic way to do it because I don't like trial and error. I'm just not a fan of trial and error when it comes to math problems. But this problem basically requires trial and error. There's really no way around it. You have to just try a bunch of possibilities and see what works out. And it's just not, I do not consider this to be a fun problem at all, or interesting problem, to be honest with you. So we're told we're going to call a fraction a over b, not necessarily in simplest form, special, if a and b are positive integers whose sum is 15. How many distinct integers can be written as the sum of two not necessarily different special fractions? All right, well, let's see. So we're looking at numbers of the form a over b, right? Where a plus b has to add up to 15, and a and b are both positive integers, right? So a and b are both positive integers, right? So I guess the best thing we can do is list out all the special fractions, right? So what would be the special fractions that we can have? So I have them written out in my notes, and I'll just kind of write them out really quick. So you have 1 over 14, 2 over 13, right? 3 over 12, 4 over 11, 5 over 10, 6 over 9. Whoops, no, I don't want plus. 7 over 8, 8 over 7, 9 over 6, 10 over 5, 11 over 4, 12 over 3, 13 over 2, and 14 over 1, right? So those are your fractions, right? Special fractions, right? And then what you can do is you can simplify some of them. Like this is what, 1 over 4, this is 1 over 2, this is 2 over 3, this is 3 over 2, 2, 4, 14, right? Now, essentially what it comes down to is just finding combinations of these that give you a positive integer. And you kind of have to use logical thinking to see like which two denominators can be added together that will result in an integer, right? So you can basically just look at ones that have the same denominators, right? Or ones where the denominators are multiples of each other, right? Right. So, well, not even that they necessarily have to be multiples of each other, but you have to make sure that when you add them, it's going to make an integer. So this is where the trial and error came in. And honestly, there's just no easy way to go about this. It was just a pain in the butt. So basically, like when you work it out, you're going to see that you can get 12 plus 11 is what? 12 plus 11 is 33. No, sorry. 23 over 48. So like one example would be 3 over 12 plus 11 over 4, which would give you what? 3 over 12 plus 33 over 12, which is 36 over 12. Ugh, sorry about that. Which is 3, right? So 3 is one possible integer you can get, right? Another example would just be doing 5 over 10 plus 5 over 10, right? Which is going to give you 1, right? You can do 5 over 10 plus 9 over 6, right? 1/2 plus 3/2, which is 4/2, which would give you 2. So you can get 3, 1, 2, right? Instead of showing all the different ways, I'm just going to list out the possible values that you can get, and I'll leave it to you to determine like what sum of fractions would result in that value. But basically, you get the following. You can get 1, 2, 3, 4, 6, 7, 8. 13, 16, 18, 28. And let me just see if that's everything. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. So you can get any of these integers as being a sum, right? I showed how to get these 3, but the rest I'll leave to you to figure it out. Otherwise, the video is going to be way too long. So it turns out that there are 11 different numbers you can make. I absolutely hate this problem. This is definitely one of my least favorite problems in the whole thing. I wouldn't say the hardest, but just in my opinion, not a great problem. It's just not a very interesting problem. But anyway, let's move on. Number 8, the largest prime factor of I can't speak. 16,384 is 2 because 16,384 is 2 to the 14th power. What is the sum of the digits of the greatest prime number that is a divisor of 16,383? Well, the quickest thing to notice is that 16,383 is equal to 16,384 minus 1, or 2 to the 14th minus 1, right? So we're looking for the largest prime factor of that number. But notice that that number can be written as 2 to the 7 plus 1 times 2 to the 7 minus 1, right? 2 to the 7 is 128. So we're looking at 129 times 127, right? Now, I know that 129 is not prime because 1 plus 2 plus 9 is 12, which is divisible by 3, right? So if I divide that by 3 with long division, right, I get, just looking at my notes, I get 43 times 3. So this number is 43 times 3 times 127. Now, you might ask yourself, is 127 prime? Well, in order to answer that, you need to think about numbers that end in a 7 that are not prime, right? Numbers that end in 7 that are not prime would be like 27, 57, 77, right? 117, Yeah, right. So what are factors of numbers that end in a 7? Well, 27 is 3 times 9, so it's just a power of 3. 57 is 3 times, oh, my brain. 57 is 3 times 19. So we have 319, right? So something ending in a 3, something ending in a 9. 77 is 7 times 11. We know 127 is not divisible by 11, right? 117 is 3 divided by 117 is 3, sorry, is 3 times 39, or, oh, 9 times 13. I see. So we can check basically something ending in a 3 or something. So the divisors have to be something ending in a 3 or something ending in a 9. And you can test them out. Like, you can divide by 13, you can divide by 23, you can divide by 19, 29. You can try dividing by these factors and you'll find that 127 has no factors other than itself and 1. So therefore 127 is the greatest prime factor of that number, but it wants the sum of the digits. 1 plus 2 plus 7 is 10. So the answer for number 8 is C, 10. Right? So again, that's another tricky problem of like having to recognize if a number is prime or not, which definitely is not always easy. Right? So that can be a little bit tricky. All right, let's see what's next. All right, number 9. The knights in a certain kingdom come in 2 colors. 2/7 are red, the rest are blue. Furthermore, 1/6 of the knights are magical, and the fraction of red knights who are magical is 2 times the fraction of blue knights who are magical. What fraction of red knights are magical? Okay. Well, we know if we let K be the number of knights, right? We know 2/7 of the knights are red, and we know 1/6 of them are magical, right? So, well, no, sorry. We know that 1/6 of the knights total are magical, right? So we know 2/7 of the knight are red, right? And then we know 5/7 of the knights are blue, right? And we know that if we take some fraction of these, right, which maybe I'll just call B. B represents the fraction of those knights that are magical, right? Remember, it said the fraction of knights that are the fraction of red knights that are magical is 2 times the fraction of blue knights that are magical. So that means I would need to multiply this one by 2B, right? And if I sum those together, that's the total number of magical knights, which would be 1/6 K, because 1/6 of the knights are magical, right? So therefore, I can then solve this, right? What's nice about this is I can divide everything by K, so the K's can cancel out, right? So I'm left with what? 4B over 7 plus 5B over 7 equals 1 over 6. That gives me 9B over 7 equals 1 over 6, which means B is equal to 7 over 54, right? But remember, it wants the fraction of red knights that are magical, which was actually 2B, right? So it's 14 over 54, which reduces to 7 over 27, right? So 7 over 27, which is choice C. And again, maybe there's another way to do this. Maybe you can use a Venn diagram. I actually tried using a Venn diagram, but I actually found it to be less helpful. I tend to be more of an algebraic type. I prefer to solve problems using algebra, even though I know sometimes there can be like a tool like a Venn diagram that might make it easier. But for me, it actually usually does not. All right, and then number 10, which actually, again, is not too bad. It's sort of like a logic problem, right? 40 slips of paper numbered 1 to 40 are placed in a hat. Alice and Bob each draw one number from the hat without replacement. Keeping their numbers hidden from each other, Alice says, I can't tell who has the larger number. Then Bob says, I know who has the larger number. Alice says, you do? Is your number prime? Bob replies, yes. Alice says, in that case, if I multiply your number by 100 and add my number, the result is a perfect square. What is the sum of the two numbers drawn from the hat? Okay, so the thing you have to do with a problem like this is you have to use logical reasoning, right? A lot of times in mathematics, and I'm always telling this to my students, like, it's not just about solving algebra problems or using a formula, solving an equation. Sometimes there's logical thinking involved, right? So think about it. If they each drew one number from the hat, right? And Alice, simply by looking at her number, cannot tell whose number is larger. Well, think about it. In what case could she tell who has the larger number? Well, if you think about it, the only way she could know who has the larger number is if she had picked 1 or 40. Because if she picked 1, then she knows Bob has the bigger number. And if she had picked 40, she would know Bob that she has the bigger number. Therefore, we know that she did. So we know Alice did not pick 1 or 40. She could have picked any of the other 38 numbers, but not 1 or 40. But then Bob, knowing that Alice does not know who has the bigger number, thereby knowing that Alice did not pick 1 or 40, knows who has the larger number. So if you think about it, well, what could that mean? That could mean, well, maybe Bob has either 1 or 40, because then clearly he knows who has the larger number. Or since he knows Alice doesn't have 1 or 40, he might have 2 or 39, right? Because think about it, if he has 2, he knows Alice doesn't have 1, so therefore he knows Alice's number is bigger than his. If he has 39, he knows Alice doesn't have 40, so therefore he knows his number is bigger than Alice's. So he could either have 1. So what do we know? We know Alice does not have 1 or 40, and we know Bob either has 1, 2, 39, or 40. But then Alice says, is your number prime? And Bob says, yes. Well, out of those 4 numbers, the only one that's prime is 2. So we know Bob has 2. Right? Okay, so now we know that. Well, then Alice says, in that case, if I multiply your number by 100 plus add my number, we get a perfect square. Right? So now we just need to think about, well, what perfect squares do we know that are in the 200s? Well, we know 225 is 15 squared, right? We know 256 is 16 squared. I think 289 is 17 squared, and 18 squared is, I think, above 300. So we know that Alice's number either has to be 25, 56, or 89. Well, we only have 1 to 40, so therefore Alice's number must be 25. So Alice has to have 25, right? And the question says, what is the sum of their numbers? 2 plus 25 is 27. A, right? So this one's pure logic, right? This one's all about logical thinking, logical reasoning, deductive reasoning, or what is it? I forget what it's called when you do contradictory reasoning. I think it's like inductive reasoning. Right? So, but yeah, it's a very, that to me is like a fun problem. I love problems that make you use a little bit of logical thinking and aren't just like plug in numbers and guess and check a bunch of stuff. Like these types of problems to me are way more interesting and more fun, I think, but they can also be much harder. So, all right. So I hope this was helpful to you guys. Again, please give me any suggestions, questions, different ways to do the problem. Let me know if I made a mistake. Love to have a sort of discussion about the problem. So, all right, I'm going to end the video now. And I will have a great day, guys.